All right, guys. Section 3.2, we're going to talk about properties of a function's graph. Okay. So in this section, we're going to learn how to determine the intercepts of a function, the domain and range of a function from its graph, determine whether a function is increasing, decreasing, or constant, determine the relative maximum and relative minimum values of a function, whether it's odd, even, or neither, and determining other information about a function from a graph, basically whatever it is we're looking for. So we've already talked about intercepts. I'll read you this. An intercept of a function is a point on the graph of a function where the graph either crosses or touches a coordinate axis. There are two types of intercepts. We have the y-intercept. And again, we've already talked about that. But if we wanted to draw a picture of a graph, let's just say, here's my graph. All right, let's have it come back up. So for this graph, now we're not talking about lines anymore. We're talking about, it could be any kind of graph. And right here, where it touches the y-axis, that's the y-intercept. And remember, this is very important, there can only be one y-intercept if we have a function, because if we had two y-intercepts, then we wouldn't have a function because it wouldn't pass the vertical line test, okay? We can have as many places where this touches the x-axis as we have. These are the x-intercepts. And again, we can have as many as there are. We also call x-intercepts zeros. And you also might hear it called roots. Okay, so these are somewhat comparable. For this class, we can call them the same. The only time they wouldn't be the same is sometimes zeros and roots won't be x-intercepts, but that's only if we have complex numbers, which we're not dealing with in this class. So you can have, so all these are really equivalent words. And the x-intercept are the x-coordinates of the point where the graph crosses or touches the x-axis. So again, just like I drew. So a function can have at most y-intercept, which is what I just said. Because if it had two, then it wouldn't pass the vertical line test. The y-intercept exists if x equals 0 is in the domain of the function. So the y-intercept can be found by evaluating f of 0, because f of 0 is the y value. So f of 0 is the y value when x equals 0, right? So we would have an ordered pair, something like x is 0, y is whatever it is, right? Okay. So, this is nice and easy. Find the y-intercept of this function. Well, we can do it two ways. If they give us a graph, we can look at the graph. If they don't, then we solve it. So first we'll solve it algebraically, which means I have 0 is equal to negative 3x plus 2. I subtract 2 from both sides, and I get negative 2 is equal to negative 3x. And then I divide both sides by negative 3, which gives me 2/3 is equal to x. And I like it better, x equals 2/3. Okay, so when x equals 2/3, we should be going through the y-axis. And that was completely my mistake. That's the x-axis. I set y equal to 0, and I get the x-intercept. So again, my apologies, but there'll probably be the next one apply. So this is the x-intercept. So we'll change this instead of everything else. How do I find the y-intercept? I find the y-intercept by saying x equals 0. Okay, and when x equals 0, I get negative 3 times 0, which is 0. So I get y equals 2, or f of x equals 2. Right? So, and that's that point, that is the y-intercept. It's this point right here is the y-intercept, and the 2/3 that we got before is the x-intercept. So again, my apologies. So when I want to solve for, when I want to find the y-intercept, I said x equal to 0. And when I want to find the x-intercept, I said y equal to 0. Okay, so I did it backwards. Again, my apologies. So x-intercept, we can have infinitely many or none. They're also called real zeros. I already told you that. And they're also called roots, which is not listed here. But if you ever hear someone say, what's the root of this function? It's really the 0. And we already talked about everything that's listed here. So here I want to find all the intercepts. So the y-intercept is always the easiest. So the y-intercept is easy because I just make x equal to 0. And you can see here, if I make x equal to 0, I have f of 0 is equal to 0 cubed minus 2 times 0 squared plus 0 minus 2. And all of the zeros just disappear and we get negative 2. So my y-intercept is negative 2. The x-intercept is a little bit more difficult because we're setting y equal to 0. So I'm going to start it over here. I think I'm going to need the room. So I have my x-intercept. To find my x-intercept, I set y equal to 0, which is the same as setting f of x equal to 0. So I get 0 is equal to x to the third minus 2x squared plus x minus 2. And now we have to factor because we have to find our factors. And there's no greatest common factor. So whenever I have 4 terms, I have to factor using factor by grouping. Now, this is not a universal truth, but this is definitely a truth for this class. There are some functions that will not work if you try to factor by grouping, and some, as I think you've seen, some functions that are not really factorable. You have to use the quadratic formula or something else, but this one should be. So we're going to separate it into 2 groups. Always put a plus between them, x minus 2. And then in the first group, my greatest common factor is x squared. I factor out that x squared and I get x minus 2. In my second group, my greatest common factor is really 1. There's no other factor there that I can take out of both terms. So I get x minus 2. Notice these two are the same. And so what I'm going to do is I'm going to factor x minus 2 out of both terms. So if I do that, I get x minus 2. And the first term, if I factor out an x minus 2, I get x squared. And the second term, if I factor out an x minus 2, I get plus 1. So now I've factored it. And we're not going to talk about complex numbers in this class. So I cannot factor x squared plus 1 because it would only be factorable if it was x squared minus 1. There's no 2 values that will multiply together to give me negative 1. And I can show you over here. So if I say, let's factor this, let's say it equals 0, then I would get x squared equals -1, and we don't have an answer to that, so it's not factorable. Okay, so that means I only have one real 0. I have one real 0. Let's see. I have one real 0 when x minus 2 equals 0. So I only have to worry about that because x squared plus 1 can't be 0. No matter what number I have, I square it, it becomes a positive number, and then I add 1 to it. Even if it's 0, that's the biggest that it could be, right? And then if I add 1 to it, it's positive, so it's not going to be 0. So I have one real 0 when x equals 2. Okay, and that is my x-intercept. So my x-intercept is x equals 2, or we could write it 2, 0. This we can write, because I have my 0, 0, minus 2. If they want an ordered pair, you write it like that. If they want just the value, you just write the value. Okay, so that's basically how you find x and y intercepts for something that looks like this. You have to factor. So now we want to determine the domain and range of a function from its graph. And sometimes this is harder than you think. So I'll try to make sure that you understand it. So this graph illustrates how we can use a function's graph to determine the domain and range. The domain is the set of all input or the x values, and the range is the output or the y values. We've already talked about that. So basically here, if I look at if I want to find my domain, I look at the area between here and here, because remember, it's the x values. So here, the interval would be a, b, including a and including b, because you can see those closed circles. Okay, the range, so this is the domain here. And the domain is my y values. So if I were to take the lowest value that it can be and the highest value it can be, all the values in between are values of y, right? Which is my range. And we can see that from smallest to biggest, it's C to D, and both of them are included. I don't have any open circles anywhere on this graph, so we're including every number between C and D. So let's do one that they're not telling us an answer for. So use the graph of the following functions to determine the domain and range. Okay, so let's start with our domain. That's my domain. And I can see that I'm going from here to here. The smallest value is -2, the largest value is 4. But I do have an open circle at -2, which means that I do not include -2. And it goes all the way to 4, and I do include 4. Okay, so that's my domain from here to here. Now let's talk about our range. Well, our range, the smallest value is on that point right there, hits the x-axis, and our largest value is right here, right? So between here and here, this is my range. Well, so my range is, well, the smallest value is 0, and there is a number at 0, so I have to include 0. My largest value is 6, and there is a point at 6, so I have to include 6. So the values that I can use to make this graph are x can be -2 to 4, not including -2. And what the answers that I'll get from that are the range, which are from 0 to 6. So if I had an equation that went with this and I evaluated and I got a value bigger than 6 for my range, I'd know I made a mistake, because it has to be between these values. All right, so let's look at B. Again, I start, let me just do it highlighted. I start here, right? And this one doesn't end. This one, if you notice, it just keeps going. See that arrow at the end right here? That means that it's not stopping at 5. It just keeps going forever. Yeah. So even though they have that x equals 5 line there, it doesn't matter. It's still going past 5 because it's going on forever. So if I want to talk about my domain for this one, well, the smallest value that I have here for my x values are -4. So we go from -4, but it's an open circle, so I don't count that. And I'm going, because of that arrow, I'm going to infinity. Okay. And my range, well, let's find the lowest value. So the smallest my number can be, it looks like right here is -3. And again, it's going to infinity. So my range here would be from -3, because it's my y values. But again, I got an open circle, so it doesn't start there. It goes right past it. And I go all the way to positive infinity because it just keeps going on forever because of that arrow. And yeah, I don't think I have anything else I can say about that. I don't know. I'm not really sure if this x equals 5 is what we call an asymptote and it's not going to go past that. If that's true, and it's not very clear, and we haven't talked about asymptotes yet. So I'm going to say, let's not make it an asymptote. Let's just say it keeps going. But if the x were to stop here at 5, then I would be going, the other possibility for this graph would be from -4 to 5, but it wouldn't hit that line. This one, I don't want to explain this, but that 5 there might possibly mean that this goes on forever, but it just goes up and never crosses that 5. It's very hard to tell from that graph. So it's either one of these two answers, and it's not very clear on this slide. All right, so example 3. This one is more clear. So this is an asymptote. If you don't know what an asymptote is, a real quick answer to that is as this graph goes more and more negative, so I'm talking about this here, you see it's going on forever, but it's never going to go past this y equals -2 line. And we'll talk about asymptotes, but not right now. So that means that if I want to talk about my domain, well, it's going on forever in the negative direction, right? So I start at negative infinity. And we can see that it's stopping at x equals 3. And there's a closed circle, so we include 3. And then my range, well, it's going down to -2, and it's going up. The highest value is 4. So it's never going to reach -2, which is a property of an asymptote, which of course you don't know yet because I haven't taught it to you unless you know from prior knowledge. But we're saying that that's the lowest it can go, and it never really is going to touch that -2. And the highest value is 4 for y, and it does include 4. So that would be the domain and range for this function from its graph. Okay, so there's a lot of writing here. And I'm gonna try to not read it all to you. I'm just gonna tell you. So we have three pieces. We have increasing, we have decreasing, and we have constant. And basically, when you look at a graph, if it's rising anywhere, this is increasing. When it starts to come down, this is decreasing. And if at this point it just went straight across, this is constant. Okay, so increasing on a graph means it's rising, it's going from left, and we always read a graph from left to right. So I start at the leftmost side, and here it's going up, and then it starts here coming back down, which means it's decreasing. And then when basically, if you think about it, like a slope, when the slope is 0, which is right there, it's a constant value. And that's what all of that basically says. So I'm not going to read it. If you want to, you're very welcome to pause the recording and read it yourself, but that's pretty much what it says. So if we look at this graph, we can see that from A to B, it's decreasing because it's coming down. From B to C, it's going straight across, which means it's constant. And from C to D, it's going up, which means it's increasing. Now notice the intervals on all of them are open. When we talk about increasing, decreasing, or constant functions, we don't ever include the endpoints. Because for example, like if I pick this point, should I include it in the decreasing or should I include it in the constant? It's really just, I consider it more of like a point of transition. So I don't have to include it in, so I'm not gonna include it in either interval. I'm just gonna say that's where it goes from one thing to the next thing, right? So we always have open parentheses for increasing, decreasing, and constant. So let's talk about this graph. So let's see where it's increasing. Okay, so let's go back to our yellow. And we can see from here, I start all the way to the left, and it's going on forever to negative infinity. And as long as I'm going up, which I just finished going up, I am increasing, right? So I'm increasing from negative infinity to, and I'm always talking about my x values. So x equals 0. And again, always open. And if I look again, I can see that it's increasing again from on that next section from, I can put a union, or I don't know if you, I don't think you have to put a union there, but you can union it from 2 to 3. And again, I never include my endpoints. So you can see it's going up there. Where is it decreasing? It's decreasing from starting here at 0, and it's going down right here. And that's really the only place it's decreasing. So it's decreasing from 0 to 2. Okay, and see, I think you can tell that I couldn't really include 2 in either interval, because which interval would I include it in? So I leave them open. And then the last thing I have is constant. And we can see that it's constant. What is this one? It's constant from here forever, right? It's just staying straight. So I start at +3 and I go to +infinity. And that's where it's constant. Basically, it's horizontal. Okay, it's not increasing, it's not decreasing. When it's not either one of those two things, then we call it constant. So then now we're going to talk about maximums and minimums. And when we talk about relative maximums and relative minimums, another word we can use is local. Because we have also something called absolute maximum, okay? So relative local means that we can actually see what's happening before and what's happening after we get to the maximum value. For example, here, my maximum is right at this point, I just made in green. And I know it starts by being increasing and then it goes decreasing, which means I have a maximum value. This is a relative max. Every maximum is a relative max. Every minimum is a minimum value, whether it's relative, but there's only one absolute max and one absolute min. And when we get to a graph that I can tell you the difference, I'll show you, but we're only dealing with relative, okay? So, that's the minimum right here. Okay, relative max, relative min. It's just the smallest value. This is the biggest value. This is the largest value. Notice that this function can equal because we're talking about the highest point. And here we're talking about the lowest point. That's the minimum. So here we have relative max. We're going to try to find on what, first we're going to talk about on what intervals is f increasing. Well, we can see that increasing, it's going up. So it's going up from here to here. And it's also going up from here to here. So I have two separate intervals. One of them is from, and these are x values, so from -3 to 2. And I can put a comma or a union, from 5, and it never stops, so it's going to infinity. So these are my two increasing intervals. Where is it decreasing? Well, it's decreasing everywhere it's going down. So here it's decreasing, and here it's decreasing. What are those intervals? Those intervals are, again, we use the x values. So we start at -7 and we go to -3. And we're also decreasing from 2 to 5, right? Those are the two intervals where we're decreasing. So the decreasing ones I highlighted in blue and the increasing ones I highlighted in yellow. And now it says, for what values of x does f have a relative minimum? So, what color? I need a new color. I think I'm done with the purple. Let's see. Let's try blue. Okay. So, relative minimum. I actually have a minimum value here and a minimum value here. I have two values where we know what happened before and we know what happens after. It's decreasing, then it's increasing, and the point where it turns, or we can call it like a turning point, the value is, and it says for what values of x. So I just want the x value. So I say -3 is one x value and 5 is another x value. And this is not an interval. These are two different x values, okay? Now, I did say the word absolute. So I have two relative minimums because I'm changing directions a lot here, right? So these are both minimum values, but that's not the minimum value of the entire graph. So the absolute minimum is this one, because I can see here that -2 is the smallest value that this graph has. I don't believe we're going to be using absolute, but I did want to talk about the differences. So relative, I could have as many as I have. Here I have 2 relative minimums, and I have, believe it or not, I only have 1 relative maximum. So I don't know if the next slide asks that. Yeah, it does. Okay, so I won't tell you ahead of time. For what values of X does F have a relative minimum? I already did that. What values of X does F have a relative minimum? I'm not really sure why it's asking me that again. It says exactly the same thing. It's exactly the same graph. So the answer is still the same for C and D. For what values? Yes. So again, it's just asking the exact same thing. So it's going to be the same, -3 and 5. Those are the relative minimums. Yes. And it says the next question is a little different. It says, what are the relative minima? So now that's a different question. The relative minima is the minimum values, which are the Y values. They're not the X values. So where does it occur? It occurs when X equals -3. -3. Yeah, so there's a minimum when X equals -3. But the minimum value when X equals -3 is my Y value, which is -2. And also, I have a second relative minimum, and this just is plural for minimum. So more than one minimum is a minima, okay? And this right here is another minimum value, a relative minimum, which is Y. So basically, let me write, these are the Y values. That's what the minimum values are. Now we talk about what are the relative maxima. And what we're asking is, are there any maximum values? Well, remember, it's really important to know that relative only means, so when I say relative, it means that I know what happens before and after the point. I'll say relative max or min, okay? So if I look at this graph, you might look at it and think that this point right here is a relative maximum, but it is not, because I don't know what happens before I see that point. And if that's the first point, then it's still not a relative maximum. I have to know what happens before and after, and I don't know what this graph is doing when it's less than -7. So I don't count that. I don't count this end because this goes on forever to infinity, right? So again, it just keeps going up. It's not a maximum because there's no value that it's going up to that we can call it a maximum. I only have one relative maximum, and that's right here. So what are the relative maxima? So the X value is 2, which is, if you see where does it occur. So sometimes you'll be asked the question, where is the relative maximum? Okay, and it's X equals 2. If it says what is the relative maxima. It's y equals 5. And I know that other places it's bigger, but neither one of them are called a relative maximum because I don't know what happens before or after. Okay, so hopefully that makes sense. Okay, so now we're gonna talk about even, odd, or neither. So again, you're gonna be seeing even, odd, or neither for quite a while, depending on how much math you're gonna be taking. But functions whose graphs are symmetric about the y-axis are called even. So this right here is an even function, because if I drew a line right down the middle, like right here, which is the y-axis, right? Then if I folded it there, they would be, both halves look exactly the same, just like a butterfly, right? A butterfly, it would be considered like an even function because if we have if we stand it straight up and we put a line down the middle, both sides should be the same. Okay. Same thing with this. This is, they're all even because they're all symmetric around the y-axis. Now, if you don't have a graph, the algebraic part is that the way you solve things algebraically is really just here. It actually tells me I don't have to rewrite it. This is what we're looking for. F of x equals negative f of x, which should make sense. Here I pick a point on this side, there's x, and I have y. If it's even, I have over on this side, the negative x value gives me the same value of y. And that happens everywhere it's even. Okay, so something that's even that you've seen, and think about why it might be called even. A parabola looks like this. It's symmetric around the y-axis. It's y equals x squared, and it is even. So you can think about even as like x squared because the exponent is even. Okay, you can't always go by that. You have to know a lot about, you have to know a lot more than that to say. You have to either know what the graph looks like or you have to know some other things. But for now, we're just going to say if I have a graph and it's symmetric around the y-axis, then it's even. If I don't have a graph, then I have to use the algebra, and I'll show you how to do that. When things are odd. So for odd functions, they're symmetric around the origin. So symmetric around the origin. So basically, the easiest way that I can tell you how to tell is if you draw this graph, any of these graphs on a piece of paper, and you turn the piece of paper completely upside down, it will look exactly the same. Okay, you can see that. Like if you want to try, look at your if you have a laptop and you can move it, or a tablet, and you turn it upside down, it'll look exactly the same. Or you can draw this on a piece of paper, turn the paper upside down, and you'll see that they look exactly the same. The algebra, which I don't see here, is that, and notice always I'm starting with f of negative x. So to find out if something is odd or even, I plug in negative x. Here, negative x, when I plug in negative x, I get negative f of x. So I don't lose the negatives here because this value will be the same as this value, except the negative x and the negative y, both things change. So notice here, I'm changing the x to negative, and that changes the y to negative, right? I'm changing the x to negative, which changes the y to negative. Okay, so now, just from a graph, let's see if we can determine what's even, odd, or neither. Well, let's look at A. Is it symmetric around the y-axis? No, because if I were to flip this around the y-axis, it would pretty much look like this, right? Which doesn't look the same. So it's not even. If I were to turn it upside down, it would not look the same. We can see this is neither. B, well, if I look at this and I turn that upside down, it will look exactly the same. This is an odd function. It is symmetric around the origin. And then C, well, if I turn this upside down, I would end up having a graph that looks like that, which is again not the same. But this one is symmetric around the y-axis, because if I look at this side, it's exactly the same as that side. So when something's symmetric around the y-axis, it's even. All right, so use this graph to answer each question. I guess the questions are coming. Oh, okay, yes. Okay, so we're gonna put it all together now. What is the y-intercept? Well, the y-intercept is right here where the graph crosses the y-axis and x equals 0, which we can see is true. So the y-intercept is y equals -2, or as an ordered pair, 0, -2. What are the real zeros? That's the same as saying the x-intercept. Remember, we talked about that. X-intercept and real zeros are the same. So we have 1, 2, 3, 4, 5. So the real zeros are x equals -6, -2, +2, +6, and 10. So everywhere it hits the x-axis, that's where my real zeros are. They're the same as x-intercepts. Okay? Determine the domain and range. Well, it looks like, let me erase all my little blue things. And it looks continuous. It means it goes on without making, it doesn't have any open circles or anything between them. So that means I go from, for the domain, I go from here to here. This is my domain, right? Where it begins and where it ends on the x-axis. So I can say my domain, where it begins is at -7, but I have an open circle. So I put a parentheses, and where it ends is at 11, right? And it has a closed circle. So I include 11. My range, again, I think I'm gonna do this in a different color. So it's going, this is the smallest value of y, and it looks like 4 is the largest value. So between those two values, this is my range. And so my range is from, the y value is -5, and I do include -5, all the way to 4. And I actually have 2 points at 4, so 4 is included. And every value between those two values are on that graph. Okay? Determine the intervals on which f is increasing, decreasing, constant. So let's talk about constant first. I don't see any place that it's constant. There's no horizontal line here at all, so it's going up and down. So none are constant. Okay, so now I'll do increasing. And it's increasing everywhere it's going up. So it's going up there, it's going up there, and it's going up there. So I have 3 intervals where it's increasing. It's increasing from -7 to -4. Remember, I use my X values. And so that's my first interval. My second interval is from 0 to 4. And my last value is from 8 to 11. And remember, always use parentheses. We never include the endpoints, okay? Decreasing. So where is it decreasing? Is decreasing everywhere it's going down. So it's going down there, and it's going down there, and that's it. So we're decreasing from x equals -4 to x equals 0, and also from 4 to 8. Okay, so increasing where it's yellow, decreasing where it's blue. I just put it in interval notation. It's simple as that. Okay, so we're still going to use the same graph. For what values of x does f obtain a relative minimum? So let's get, I think I'll do it with a highlighter. So where's there a relative minimum? I can't count endpoints because I don't know what happens at those endpoints. Remember, I have to know what happens before and after. And the endpoints, so this one I know what happens after, but I don't know what happens before. And this one I know what happens before, but I don't know what happens after. So I can't count those. All I'm going to count are the relative minimum are here and here. I only have 2. And those are where, for what values of x. So now I want x equals 0 and x equals 8. Those are my 2 minimum values. Those are the values where x is, so this is where, so for values of x. So that's another way to say it for what values of x. Sometimes you will see it. Where is the relative minimum? Then I'm going to talk about my x values are where. Notice here it says, what are the relative minimums? What is the actual value of the minimum value? That's what y equals. That's going to be -2 and -5. Those are my 2 minimum values, and those are relative minimum. Relative means there's more than one, okay? And then we want to know, is f even, odd, or neither? Well, is this symmetric around the y-axis? Absolutely not. If you break this at the y-axis, the right-hand side does not look like the left-hand side. So we know for sure it is not even. Is it odd? Well, you would probably have to draw it and turn it upside down. But I should, if it were odd, and I have this point, let's say, for example, I have this 0.42, I should have another point on the other side of the y-axis, which is -4, -2. Remember, everything's going to be negative. And if I go 1, 2, 3, 4, and then I go -2, that would give me a point right there, which I don't have. So we can say for sure it's not negative. I mean, I'm sorry, for sure it's not odd. So if it's not odd and it's not even, it's neither. Okay, and that concludes 3.2. So thank you for listening, and I hope that everything made sense. If not, please don't hesitate to ask. Thank you very much, and I'll be doing 3.3 in a minute. Okay, bye.